Okay, so we're happy to have Max Lieblich to talk to us about infinite rank vector bundles and applications.
Thank you so much for the invitation, and thank you for running this thing for all this time. It's a real service to the community, and we've been lucky to have the ability to do this in the middle of such a complicated time. I'd like to talk to you about joint work with de Jong and Shin. So Johan de Jong and Min-Sun Shin. And it's mostly a discussion of something that's very strange that came up in our attempt to think about a famous old problem of Grothendieck and also other questions that have been raised by Totaro and others. But there's not going to be like a definitive answer to a question. It's more going to be a bunch of questions and sort of strange observations. Before I get to the weird stuff, I want to kind of tell you where this ancient question, this question of Grothendieck comes from. I know a bunch of people here are well aware of what I'm going to say here at the beginning, but I think there are others who aren't. So I'd like to kind of just remind you to put a framing around the basic question I want to address here. And really, with so many talks about something like the Brouwer group, we have to go back to 1843 and think about the first time anyone discovered one of these interesting division algebra. So the origin is really this discovery in 1843 of the quaternions. Okay. And we know this is an R algebra generated by two square roots of unity of -1 that anti-commute. Again, this was a big thing when it was discovered, right? And there's a very interesting history of it that I will not talk about. And people actually were sort of just enamored of this thing, didn't realize its limitations until around 1878. So it really was the first kind of interesting example of something of a non-commutative algebra that people were really grappling with. But from the point of view of what I want to say today, the kind of thing that the basic fact about it, the sort of key fact, is that it has a geometric meaning. And the algebraic avatar of this key fact, which was discovered relatively early on, is if I extend scalars to the complex numbers, this becomes isomorphic to 2x2 matrices over the complex numbers. That is to say, if you were to try to form the quaternions over the complex numbers, you just get a copy of the ring of 2x2 matrices. And this has two geometric avatars that are sort of useful, one being more useful than the other for the purposes of what I want to say today. So kind of let me point this out. Any K algebra, so any algebra over a field, let me start there, that has this property that becomes isomorphic to some n by n matrix algebra over the algebraic closure has two kind of standard geometric avatars, a big one and a small one. Okay, and the first one is one that you may have seen more frequently in your lives, and that is what I'll call the large one. I can form the scheme of isomorphisms from A to n by n matrices. So this is a functor that over a K scheme gives the set of isomorphisms from A to Mn of O, right? And this is a left PGLN torsor. Here we're using the Scullum-Noether theorem, which in part, which says that the automorphism scheme of n by n matrices is PGLN. It's units of the matrix ring acting by conjugation gives all the automorphisms locally. It's over a field, the automorphisms arise that way. And so any two isomorphisms from A to Mn, they differ by an automorphism of Mn, and so that's the PGLN structure that makes this into a torsor. And it's a torsor because we've specified that there is actually a geometric point of it there. All right. So this is like the large geometric incarnation of this thing. Of course, this is related to the Brouwer-Severi variety. Descent theory connects all these different things together. I'm not going to talk about that today. But I will point out here that one thing you get from this, since we know what torsors are, we get here a class called the class of A in H1 spec K PGLN. right? I mean, there it is. There's a comma that this is a sort of a tautological just restatement of what I just said to you. It's just symbolic. Okay. So that's the large geometric avatar of this algebra, and there's a small one too. In fact, there's one that's negative dimensional. And it's a stack. So we can define a stack on spec of K, the big site. So let's call the stack curly X. Here's what it is. The objects over Y are pairs V and phi. So here, V is locally free of, I don't know, well, whatever, locally free OY module. And phi is an algebra isomorphism. So instead of saying, yeah, this thing, how does this become MN? We're saying to sort of just consider all the ways in which it becomes MN, and that's a stack. It's not just any stack. Again, the Skull-Noether theorem tells us it's a GM gerb. X is a GM gerb. The funny thing is, now that it's, what year is it now? 2022. You can just say something like GM gerb. But in 2005, if you said that in a talk, you'd have to spend 5 minutes explaining what that meant. Okay. So again, we know in the similar way that H1 classifies torsors, Giraud taught us that H2 classifies gerbs. So again, here we get a class of A in H2 spec K GM. Okay. And there's something special here. There's one other kind of special piece of structure that happens in this stack, in this small stack, the small geometric version of A. Because X is a moduli problem, it's the moduli problem of realizing A as the endomorphisms of a vector bundle. It comes with a universal solution. So there is a vector bundle, a locally free sheaf, V on the stack, and a sort of universal phi from A base change to the stack, mapping isomorphically to N to V. Or if you like, we have that. No, I forget that. I'll come back to that later. And this is not a random vector bundle. This is a special property because of the sort of the universality and what the stack is. The inertial GM action on V is just scalar multiplication. And now if you're being very careful, I mean, the left action associated to the canonical right inertial action where you have to use the inversion map, otherwise you make a sign error. There's a name for these things. This is called being a twisted sheath or twisted vector bundle or whatever, okay? So we've got this torsor, we've got this gerb, we've got this universal twisted vector bundle thing. And of course, these two realizations are connected, linked. If I think about just the usual presentation of PGLN, I have a boundary map. H1, I'm omitting the space here for the sake of not having to write spec of K over and over. And as you'd guess, and this is a horrible, horrible abuse of notation that Kevin Buzzard would be very angry about because the computer would break if I tried to say this. The class of A goes to the class of A. All right, so these things are realized in the usual way, and it makes sense if you just sort of think about what it could mean to sort of try to reduce the structure group of the torsor to GLN. You end up running on the stack also, so it's sort of it's all compatible. Okay, so far so good. What questions do you have about anything I've said so far? I'm happy to address anything.
Max, what is a GM gerb?
Dan, do you really want me to explain?
I had to break your spell.
Okay, I don't want to explain, but if you really want me to, I will. So
no, that was a joke.
Thank you. Okay, right. So let me tell you a classical theorem that I'll say it in a certain way, which is not like the full statement of the classical theorem, but for the purposes of what I'm talking about today, I'm going to phrase it like this. So the classical theorem says, now you see, for many algebra, which is this sort of exotic looking weird thing, we get an element of this cohomology group. And this is a nice, I guess you could imagine this is a better place to think of an invariant because it's like a nice abelian group. It also makes no reference to n. So you've lost a lot of the structural data about A as you pass to this class in this abelian group. You've kept a lot more structural data here. You can see that going from this big positive dimensional torsor that's remembering in its dimension things about A to this thing that's sort of a more bizarre object of dimension -1. So the classical theorem says that every class alpha in H2 spec K GM is the class of A for some A. Yeah. That's the, now let me show you a modern proof of this. So we can choose a finite field extension L over K splitting alpha. And so what this means is that if I restrict alpha to L, it's 0. So if I take the gerb and I base change it to L, it becomes isomorphic to BGM over L. And now the standard character chi of GM gives an invertible twisted sheaf on BGM over L. That is to say, a twisted vector bundle of rank 1. And now we can push forward by the projection map to get a twisted vector bundle on, curly X. It's going to have some bigger rank. The rank is going to be the degree of L over K. And so let's call this twisted vector bundle, I don't know, say V. If I take pi lower star of n to V equal to A, so here pi is the map from curly X to spec of K, this works. All right. More generally, I guess it's worth pointing out, more generally, the statement, the existence of these twisted vector bundles, I mean, what this is sort of hiding in what I'm saying here on X is like equivalent to the existence of an A over K. Okay, so we're really, from this point of view, I guess there's some themes hiding in here that'll come up again later. You split the class where you understand the structure of the sheaves on the thing, and then you start pushing forward to get a nice sheaf downstairs, and that gives you this algebraic structure that you're interested in. Okay? So controlled splitting produces algebras. And the key about how we're splitting is it's the finite freeness. The finite freeness, is that, I don't know if this is a mathematically correct. Finite freeness of L over K, or maybe could be slightly more pedantic, of spec of L mapping to spec of K produces the twisted vector. And we're pushing forward along a very nice map to get a sheaf with very nice properties. Okay. So that's a modern proof. There's many ancient proofs of this. They work very differently. You can try to write things down explicitly with Galois cohomology and so on and so on and so on. Lots of beautiful theory going back more than a century. Really wonderful stuff worth learning about. Okay. Now, over time, people started trying to generalize these ideas to understand algebras like this over rings or over other kinds of over topoi, and I can't even list the total collection of people who've thought about this. But I do want to kind of zero in on sort of the ultimate geometric generalization of all this due to Grothendieck. Okay, so I mean, the Auslander, Goldman, Azumaya, many other people thought about this from an algebraic point of view over rings, and then Grothendieck realized that this is actually really a geometric thing that you could do over a scheme or a ring types. So here's a kind of higher dimensional generalization. And then it gets more interesting. So this is due to Grothendieck. But you'll see that he's naming things after Azumaya because it's not entirely due to Grothendieck. Nothing in mathematics is entirely due to one person. Okay. So let me tell you what the replacements are for these algebras that we're interested in. And then I'll tell you what the replacements are for the statements we're thinking about with respect to which group elements come from these sorts of algebras. So definition. I'll just do this for schemes right now, or an algebraic space. Given a scheme, X, or algebraic space if you want, or stack or whatever, an Azumaya algebra, of degree n is an OX algebra A such that let's see, that becomes isomorphic to Mn of O over an étal covering of X. Or ring this suitable totals. Okay. And now, for those of you who are worried, N is a global section of the constant sheaf Z. Okay. Right. So, but if you let's not be weird. I mean, let's just think about varieties. Okay, I don't want to just think crazy. If something weird happens in a boundary case, I don't want to deal with it. So, just like before, the thing is, I guess what I'm saying is what Grothendieck realized is that the key property, these algebras, like the quaternions, they have all sorts of other things you can phrase algebraic with. They're central simple algebras. You can talk about ideals, you can talk about this, you can talk about that. But it turns out that all the algebraic conditions are equivalent to this descent theoretic or geometric condition, this condition about the geometric fibers, about what this is a bundle of, and that's what Grothendieck realized we should be saying, is that that's the intrinsic thing that really is the important property of the algebra. It's a form of a matrix algebra. It's a bundle of matrix algebras. Okay, and for such a thing, again, we can make these large and small geometric avatars. So we get a class of A in H1 of X with coefficients of PGLN. Again, like the étal topology or whatever. Let's just keep that one in mind if that's the one you like. And also a class of A, which I'm writing with the same symbol, in H2 of XGM. All right. Okay. Now, one thing you should know about this is that n times the class of A is equal to 0. In H2 of XGM. Here, this is where I don't want anybody to say, I don't want to get involved with this right now. Okay, please don't say anything about that. This is a torsion class. Now somebody would say, well, what if X is not quasi-compact and N has increasing orders and everything? But let's not, I don't want to.
Or you're allowing different N for like different connected components of X?
That's you're doing. I guess I asked for this, didn't I? Let's say N is. Let's just say X is a variety. Okay, and it has only one connected component. Yes, I mean, good question. Yes, but no. Let's not deal with that. Good question. Thank you. So you get a torsion class this way, or at least locally you get a torsion class, and so if you want to think about, okay, so let's see here. Before I ask, well, okay, let me say one other fact here before I ask the key question. So you've got this torsor, it gives rise to this gerb. So again, we have this universal sheaf on this thing X, this gerb of what's called a gerb of trivializations. We have this universal V and an isomorphism A restricted to X at the end of V. Okay. So you've got this, and it's a twisted sheaf, twisted vector bundle of rank N. Okay. So again, we could ask this question. We could think about this key, beautiful classical theorem that said every cohomology class arises from some algebra. And that's an amazing thing. You can interpret the cohomology group in terms of these non-commutative algebras. So we can ask ourselves again, is this still true? Right? This is Grothendieck's question. Okay, so Grothendieck's question is every torsion class in H2 of GM of the form, is every torsion class the class of A for some Azumaya algebra A? All right. And as I've been kind of hinting at in the way I've been talking about these things, and this is what's really fascinating about this, equivalently, does every torsion GM gerb curly X on capital X admit a non-zero, a non-trivial, and nowhere zero twisted vector bundle? So you can see that this is actually like a lot more interesting. Saying that the cohomology class is associated to an algebra, I mean, it's already an interesting question, I think. But realizing that that's the same as saying that there is a vector bundle on this space somehow makes it feel like fascinatingly bizarre. Because of course, there's always vector bundles on any space, any ringed space. I mean, on any, you just take, trivial vector bundles are there. So there's something really interesting about the fact that here, the vector bundle has to have this action of the stabilizer, and that puts some kind of restriction on what's going on that makes it highly non-obvious. Okay. So a lot of people have thought about this question, right? Many people have thought about this. Again, I don't have it. I don't think I have an exhaustive list, so I'm not going to pretend to have an exhaustive list. Many people have thought about this, but I want to say at least some of the people of whom I'm aware. And I apologize to anybody who's not in this list. It's not because I think you're not a great mathematician. So here's some of the people that I know have thought about this over time. Gauber, this is famously his thesis. I'll talk about that a little bit in a second. Edidin, Hassett, Kresh, Vistoli wrote a nice paper about this. Schröer has thought about this for surfaces of various kinds. My student Sid Mathur has thought about this. Vincent Shin has thought about this. A bunch of dots. I'm sure that half the people here know more about who's thought about this than I do right now. But let me tell you some of what we know. I guess Totaro has thought about this in a different form. Maybe everyone's thought about this. It's like the Jacobian conjecture. Not everyone will admit it, but everyone's thought about it a little bit. So here's what we know. And this list of things is going to look redundant because some of them are redundant, but this is a little bit about what different people proved at different times. Sometimes they got subsumed in subsequent things. And this is not in historical order. Oh, Grothendieck thought about this. Sorry. When he first thought about this, he thought about this. All right. So I'm going to write these sort of in a random order, just so you have some sense of the limits of what we understand. So the first is, if X is affine, then yes. When I say yes or no, or not necessarily, I mean the answer to this question. Does that make sense? So if it's affine, we know that every torsion class comes from one of these babies. Similarly, if it's a separated union of two affines, okay, this is Gauber's thesis. If X is quasi-projective, then yes. And what I really mean is if it has an ample invertible sheaf. Okay, so you have to be a little careful what you mean by quasi-projective. Okay, this is also Gauber. It's a famous result of Gauber. He never published it. De Jong wrote up a treatment of it using twisted sheaves. He never published that. Okay, in Grothendieck's original work, let's see, we have that if X is regular of dimension less than or equal to 2, then yes. Okay, what else do we have here? If X has dimension 1, I think I'm saying this right, has dimension 1, no regularity assumptions or anything like that, then yes. 5. If X is a, let's see, a normal separated surface, then yes. And when I say surface, I mean, you can think about what I mean. Think about algebraic, like just algebraic surface. Don't think something weird. Okay. 6. Maybe it's just always yes, right? Everything I've said here is yes. So maybe it's just always yes. No, but the answer is no. It's not always yes. Okay. If X is not separated, there are two-dimensional examples. This is edited in Hasid-Kresh-Vistali, then not necessarily. And their example is not that bad. You just take cones and glue them together away from the cone point, and then you can make an example that can't come from an algebra. Okay. What we don't know for a quasi-compact, quasi-separated scheme, or maybe for any quasi-compact separated scheme, I guess the conjecture is that it maybe is still true, but we don't know. But here are the two like biggest outstanding cases, so like the lowest hanging fruit, the lowest hanging unresolved fruit. Okay, and one of these is incredibly frustrating. They're both very frustrating. So one, X smooth, non-projective, non-quasi-projective, threefold. Okay, we have no idea. We have no idea. The other one is X admits not an ample invertible sheaf, but an ample family of invertible sheaves. When you see de Jong's proof, for example, of Gauber's results, the quasi-projective case, the proof goes by sort of trying to like take affines and constantly enlarge a locus where your sheaf is locally free by looking at like Bertini results for general maps. And you start to think, well, what if I just have an ample family? Surely there's something, some trick I could. No, nobody can figure this out. It's really frustrating. Okay,
Max, what's an ample family of invertible sheaves?
It's if you want to resolve, it's a family of invertible sheaves so that you can, for any coherent sheaf, you can find a sum of powers of them that surjects onto it. So it's sort of like if you have an ample sheaf, you can just take a sum of powers of this one sheaf and surject onto any sheaf with it. But you can't necessarily, for an ample family, you can't rely on any one of them. You have to rely on all of them together. So the example that you should keep in mind is if your scheme is regular, then the set of line bundles is an ample family, because you can any divisor is Cartier, and so if you take like sections over affine, the complement of an affine is going to be a Cartier divisor. You can use twists of the line bundle to cancel poles of sections, and so you can generate a sheaf by just adding up copies of these various line bundles and using them to sort of cancel out the poles of sections and use affine generators. Does this make sense what I'm saying here?
Yes, thanks.
Yeah, okay. Right. There's not like one giant line bundle whose powers are going to contain all poles. That's how you should think about the difference. Okay. Great. So one feature that I think is worth pointing out here, now there's something bizarre when you look at Grothendieck's question and you look at like the whole setup, it might make you might wonder like why things are torsion. Like what does it mean, the torsion hypothesis? So I just want to point out there's like a weird feature of the situation. The first is that if X is a smooth variety, then the cohomology is all torsion. Okay, so in some sense, we're not really talking about the torsion classes, we're talking about all the classes in that case. But, and this might not make you feel weird, but if we look at the, let's say, X is smooth over C, if we look at the analytic version of the Bauer group, it need not be torsion. And so, depending on what you think the difference should be between the algebraic and analytic situations, something looks a little fishy, right? You might wonder you might wonder from sort of thinking about this, like, are Azumaya algebras the right model? Right. Okay. So, Azumaya algebras are related to vector bundles of finite rank on these gerbs. Of course, you could take coherent sheaves. Those gerbs always carry lots of coherent sheaves of positive rank. That's not very hard to show. But those are a little floppy. You could ask about like perfect complexes. Well, a coherent sheaf is a perfect complex. So there's always like a derived model of Azumaya algebras that just always exists for any class. So either that means it's the right model or it's like too flexible. For the derived model is maybe like so flexible that you're not saying anything. The classical model is so rigid that maybe you're too constrained. So the question is there something kind of in between? That's really what I'm talking about here. And I think it's kind of interesting. All right. Okay. So I want to kind of focus on two examples here that I think are going to illustrate two interesting features of what I still haven't just told you what I'm going to really talk about yet, but there's these two examples that I think will be interesting to think about once we've gotten to kind of the main event here. So first of all, I want to give you a rough idea, very rough idea of the affine case of Gauber's proof. I'm not actually going to explain anything, but so here X is spec of A, and alpha is some torsion class in its cohomology. All right. And the question is like, how do you want to find this vector bundle on the stack? Okay, so what do you do? All right. So there's two extremely clever things that happen. All right. So the first one is that you can show that shows Zariski local existence. Using this crazy trick. So let's see. You find sort of xf's inside of X so that there exists Y to xf, which is finite flat, and alpha restricted to Y is Zariski locally trivial. Oh, sorry, I shouldn't have written the word show. Hold on a second. So you reduce to the Zariski, reduce to the case where Zariski locally, we know we have the thing. And the way you do it is you find Zariski opens where there's a finite flat cover on which it's Zariski locally trivial. And now we just talked about how if you have a finite flat cover, you can push forward vector bundles to get vector bundles, right? Finite flat, if you push forward along a finite flat map, a vector bundle goes to a vector bundle. Just remember this. I'm saying this over and over for a reason. And that reduces you to the situation now where it's Zariski locally trivial. So we've now reduced ourselves to the case where it's Zariski locally, we know the solution exists. Okay. And then the second thing is, now what do you do if you've got this cover where you've got this Zariski, assuming Zariski local solutions, we solve in general by gluing. So we should need to glue them, somehow glue them together. And there's a subtle point, which is if we have V1 on XF1 and V2, whoops, V2 on XF2, then if we think about what happens on XF1 intersect XF2, we've got V1 and V2, there's no reason for them to be isomorphic. So we somehow need to reconcile the differences between the two. And that usually involves tensoring by some locally free sheaves that aren't twisted to kind of make things line up. And you have to understand things about the K-theory of affines and what happens in the K-theory ring. So, okay, this is the other brilliant part of Gauber's argument. But there's some way you have to reconcile these differences. Okay. So that's one thing I want you to understand. The key thing here is it's this combined with, so the finite flat business combined with this reconciliation on an affine. And there's another thing that I think is an interesting example that's worth sort of pondering for a second. Okay, and I love this example. Okay, so say that we've got that our X, we've got a singular surface with, one singular point. So this is a resolution of a singular surface, or a singular point on the surface. I really just mean it only has one singular point. I mean, that's the case I'm interested in. So for example, you could, and say that that the genus of C is bigger than 0. So you could, for example, take a cubic in P2 and blow up 10 points, and then you can contract the strict transform of this genus 1 curve, and so you'll contract it to an elliptic singularity that has this positive genus curve as the exceptional fiber when you resolve. All right, and let's say that let's assume that, I don't know, H1, there's lots of assumptions you could make here. I'm just going to assume this one, H1XO to H1COC is not surjective. For example, if X is P2, if you start with P2, then H1 of X is going to be 0. Okay, that's the sort of, okay. Now, the Leray spectral sequence, what does it do? If you think of what's going on, you get this map from pic of C, modulo, so to speak, pic of X restricted to C, you know what I mean, the image of pic of X in C, mapping to H2 of X bar GM. Right, we're trying to make these classes in H2 of X bar GM is what I'm trying to tell you. One way to do it in this situation where you have a resolution is if you take line bundles on C that are torsion, they're going to give you torsion classes in this cohomology group, the things that we're interested in. All right. And so we could ask Grothendieck's question here. If I take an L in, say the N torsion, just to be concrete, of this that's not in pic of X restricted to C, I hope you know what I mean when I say this. Okay, we get some interesting alpha in H2 of X bar GM bracket N. And, you could ask, does this satisfy Grothendieck's thing? Is alpha equal to the class of some A? So far, so good? I'm just making an example of a class. So here's how you do it. This case, we can be very explicit. There's a standard trick, beautiful trick. Have you seen this trick before? If I take L to the plus N, this is a vector bundle on C, okay, because the determinant of L to the plus N equals OC lifts to X, we know that this L to the plus N lifts to X as some vector bundle, V. So there's some vector bundle in X whose restriction to the curve is just a direct sum of copies of L. All right. And now, let's see, let's call this map rho. Fact. This is not too hard to show. Fact. If I take the sheaf of endomorphisms of rho lower star of V, this is an Azumaya algebra with class alpha. I love this example. It's a great example because it's almost a vector bundle, right? You're like, well, why isn't this the trivial Azumaya algebra? Why isn't this endomorph? Because rho lower star of V is not locally free. It's reflexive, but not locally free. So even though this algebra is endomorphisms of something, it's not a trivial Azumaya algebra. Now, again, if you were to take a random line bundle on C, it's not going to be torsion. You'll get some non-torsion class in H2 of X bar. We also know that you can't add up a finite number of copies of a non-torsion line bundle and expect its determinant to lift to X. Okay. So this is something we'll also come back to again in a moment. All right. Questions, comments, thoughts, or feelings about something I've said since the last time I asked you for your questions?
I didn't quite get why does given that the determinant lifts, why does this vector bundle itself lift to X?
It's a beautiful argument. So I'm using, okay, I'm going to assume here that X is projective because that makes this easier. The trick goes like this. Okay, let me explain. So the trick, so the claim, if I've got C and X and I've got W on C. And X is projective, so I've got O of 1 on X also. So floating around, we'll use this in a second. If I've got W on C such that det W lifts to X, then W lifts. So let me just sketch that. If I think about a general map, let's say that the rank of W is R. If I think about a general collection of R-1 sections of a large twist of W, they're going to be linearly independent at every point. It's a Bertini theorem. So now, by assumption, this lifts to X, some curly L on X. This lifts to X, And so you might be like, oh, hey, maybe I can lift the extension class, right? This corresponds to some class in H1 of C, L dual to the R-1. Okay, so the first thing you think is naively, well, maybe I can just lift this through this map. Okay, well, you can't do that. That's crazy. That's not going to work. But here's the trick. The trick is that what you can do is you can remove 1 point from X that's not in C. Just take a point out. Now, you may be aware of the fact that when you have a non-projective, quasi-projective variety, say, no coherent sheaf has H2, has top cohomology. That's actually a criterion for projectivity, for properness. And so then we know that H1 of X minus little x, L dual to the R-1, does surject onto H1 of C, L dual to the R-1. And so we can lift the extension to X minus little x. And then we can just take reflexive hull and sort of take reflexive extension of the middle part. Do you know what I'm trying to say here? We've got like OU to the R-1 goes to some curly V, goes to this L, goes to 0. And if I just take V, I don't know, I lower star of V, this is sort of a lift of W of n. So here I is the inclusion of X minus X, you can call U into X. If I just push forward this V, this lifts W of n. Have you seen that before? Does that answer your question?
That answers my question. That is truly crazy, but okay.
Isn't that an amazing argument? I love them. Okay, this is also good, and I'm really glad you asked because that's going to come up again later too. If I manage to get to what I want to say, all right. So it's super amazing. Okay, love that. Great, thank you so much for asking. I just love that. Okay, so like I said,
sorry, just a quick question. Does the same thing work with in higher dimension if you leave out the codimension 2 thing? I mean, the reflexive part does, but is that cohomology thing true? That if you're missing a codimension 2 thing, then probably not. But
I don't think so. No.
Yeah.
I don't think so.
Okay. Yeah, daydreaming.
Right, and then, but as you point out, you're screwed at the last step, even if you manage to do some good lifting. Sid, my former student Sid did show something interesting about threefolds this way. Like he showed that things happen away from, or maybe he showed some things happens away from codimension. Codimension something. It must be 2 by similar kinds of arguments. Okay, so you could look at his paper to see what he did. So great. So now I've told you a couple of examples. I've told you something about how Gauber's theorem works. I've told you the importance of finding covers that split cohomology in certain ways. I've told you about examples where you have curves contracting, but you can also make non-torsion classes in a similar way. And there's this vector bundle lifting problem that seems related to all of us. Right. Now I want to tell you, like, you might be motivated to think about like some kind of non-torsion formulation of Grothendieck's question. Non-torsion version of Grothendieck's question. All right, and I mean, here's the craziest way. Here's the craziest way to say it. So suppose now X is a scheme. Really, just take it to be a variety. Right? Alpha and H2 of XGM, not necessarily torsion. Okay. So first, I want to define. There's 2 ways you could do this. This is the one that looks more insane. what should an Azumaya algebra of infinite rank? Oh, maybe I didn't make this clear. If we're going to do a non-torsion version of this, then maybe we should allow infinite rank things instead of finite rank things, because it's sort of infinite. It's infinity torsion, so the rank should be infinity, right? So an Azumaya algebra of infinite rank, is that too abbreviated? Is a sheaf, and I'm only going to consider countable rank for technical reasons, is a sheaf of OX algebras on the big side, I don't know, say big étal side of X, that is locally isomorphic to the sheaf of endomorphisms of a direct sum of natural numbers copies of O. Okay. Now this is like not at all quasi-coherent. Okay, this is a terrible thing. You need to use the big site if you want to do this, because it's a, you know, forming endomorphic, dualizing is a terrible thing to do. So you shouldn't think about this on a small site. You'll cause problems for yourself. But on the big site, you can just say that this thing is what you think it is. It's just a highly bizarre algebra. All right. But now let me tell you, you know, is there like a Skolem-Noether theorem for this infinite dimensional matrix sheaf and all this stuff? So theorem 0, which is really what connects this to geometry. And I guess you could trace this to Skolem-Noether, sorry, Courtemanche, Degas, De Jong, myself, and Shin, is that the Skolem-Noether theorem still works. So the automorphisms of the endomorphism ring in this crazy sense of O to the plus n is GL infinity modulo GM. And I'm using like capital N because I just, that's the infinity I mean. So sometimes this is just GL infinity. Because that is to say, i.e., every automorphism is inner. That's really what this is saying. And the scalars are the center, you know, the thing that die when you take the conjugation. All right, so corollary. Every infinite Azumaya thing, A, has a GM gerb of trivializations. And of course, you know, computing the cohomology of GM, you can do it on the big site, you can do it on all the different sites. So we're not changing what the cohomology target is here when we do this. Okay. So now Grothendieck's question we could ask is every alpha in say H2 of XGM, now forgetting whether or not it's torsion, equal to the class of A for some, you know, some A, but now A could be an infinite rank Azumaya algebra. And you could ask the same thing for analytic spaces or topological spaces or manifolds or whatever. Okay. Okay.
What is GLN? Sorry,
It's,
this is a stupid question, but how do you multiply matrices with, you know, infinitely many columns?
Yes. Okay. So you've just observed that it's not symmetric. That GLN has an asymmetry. So every column has mostly zeros for a matrix in there. So it's the automorphisms. All I mean is the automorphisms of the infinite rank module. So every element has the infinite direct sum. So every basis vector can only go to something that has a finite expansion. But there's infinitely many basis vectors. So the rows can have infinitely many non-zero entries, but the columns can't. And then you can do it. Then you can multiply the matrices together. Right. So maybe one thing I should point out here, which I'm afraid I'm not going to have time to use this, but here's a crazy fact. And this is closely related to this thing about vector bundles I just mentioned to you. If I have a surjection of rings, this is a crazy fact that's also in our paper. I don't think this was not written down somewhere else we could find. Okay, surjection of rings. Then if I take GL infinity of A mapping to GL infinity of B, this is surjective. Okay, the reason that I put two exclamation marks there is this is very false. Very false for finite, you know, for GL n of A mapping to GLN of B, for example, GL1 of Z mapping to GL1 of FP, that is very not surjective. But if you do GL infinity of Z mapping to GL infinity of FP, it is surjective. And it's that asymmetry in the infinite matrices that gives you you have a huge amount of leeway that you don't have for these finite groups to do all kinds of crazy things. Right. Okay. So I mean, maybe now I'll just mention like the corollary of this that I won't have time, I think, to go to discuss in any detail is if you have C inside of X and you've got V on C, an infinite rank vector bundle. And I say again, countable, infinite rank vector bundle. Okay. X is a surface. X is a projective surface. Okay. Then there exists a finite set, a finite Z inside of X that doesn't intersect C, and they lift a V to X minus Z. You can't have a condition on the determinant because the determinant doesn't make any sense for an infinite rank vector bundle, but then there's actually no condition. Any infinite rank vector bundle lifts off of the curve to most of X, but this is even worse. But again, there's a horrible thing that happens. Infinite rank vector bundles on X minus Z need not extend to X. So there exists, for example, an infinite rank vector bundle on P1 that is not a sum of line bundles. And this implies that there exists an infinite rank vector bundle on A2 minus the origin that does not extend, that is not free, and so does not extend by Bess's theorem. Sorry, now I'm just completely short-circuiting what I was planning to say here. But so, like, one fascinating question here, if you're following along, is for an infinite rank vector bundle on C, there seems to be like, is there some reasonable codimension 2 sort of invariant obstruction? I don't know what to call it. Invariant / obstruction to lifting to X. There's lots of ways you can make this Z. Okay, you can write down. You just take two, very sort of random. Well, it's the intersection of two ample divisors, or two very ample divisors of your choice. So there's lots of ways to make that Z, but it tells you there's some kind of weird codimension 2 phenomenon that's obstructing the actual lifting of the vector bundle that pushes the obstruction away from C itself. So I think there's actually some kind of a fascinating question there. I don't know. I don't have any idea how to answer it. But so yes, Zenobi, thank you for asking about what GLN is. So now let me tell you like the main point. I think I'm ready to kind of at least express the main point here. Right. So what did I say? I told you what an infinite Azumaya algebra is. I kind of told you a version of Grothendieck's question. Then I had a digression. There's some fascinating things about infinite rank vector bundles and GL infinity. But I want to kind of just tell you, this is this key observation that Min-sun made. Observation of Shin. I mean, this is the observation by Shin. Not like, okay. Suppose X has an ample family of invertible sheaves. Then there's a Thomasson generalized Joannellou's trick to kind of show that there exists a T mapping to X such that, okay, T is affine, and this is an affine space bundle. So there exists this Zariski cover of X by UIs such that T restricted to UI is isomorphic to AN over UI. Now remember, before we were thinking about finite flat maps, pushing forward vector bundles to vector bundles, right? But there's another kind of map that pushes forward vector bundles to vector bundles. It just means that when you push forward a vector bundle, you get an infinite rank vector bundle. Okay, so like note, if I do f lower star, let's call this f of OT, this is going to be an infinite rank vector bundle on X. For example, if I push forward, you know, O of affine space, this is isomorphic to O to the capital N, because you just break down polynomials, you know what I mean? So there's a name for these morphisms due to Reynaud and Grusin, I think. So a morphism, F from T to X, is affine pure if F is affine and F lower star of OT is a locally projective O module. Okay, and locally projected, you can think of as locally free in the cases where, you know, things are sufficiently Noetherian and nice. So forget about the difference between projective. You can read in our paper, there's a long discussion of what all this stuff actually means. Okay. All right. So now the idea of the main theorem, I can say it in the last 2 minutes. Okay, I can tell you what the results actually are. So first of all, theorem 1. I wish I had more time to talk about the weird phenomena, but you can just look in our paper; they're in there. So here's theorem 1. This is the analog of Gauber's theorem. If X is affine and Noetherian, then any alpha in H2 of XGM is the class of some infinite Azumaya algebra. That is to say, there's an infinite rank, locally free, twisted vector bundle, right? So, i.e., any GM gerb carries an infinite twisted vector bundle. Okay, and the idea of the proof is it's like Gauber, but use affine pure instead of finite flat. And the reconciliation problem on affines that Gauber had to deal with all this K-theory stuff is much easier because there's an Eilenberg swindle. Okay, so that's the first thing. And then also there's a twisted Eilenberg swindle that solves the reconciliation problem. Does patching, does gluing. So the fact that things are actually kind of unique when they have infinite rank. Do you know what the Eilenberg swindle says? Oh, okay. You can take an infinite direct sum of copies of a thing and it's isomorphic to the, you know. Okay. Corollary. Sorry, I want to just state this so I can at least say I said this. Okay, corollary. If X admits an affine pure cover by an affine, then any alpha in H2 of XGM is the class of some infinite Azumaya algebra. Again, by pushing forward, because the map is affine pure. So for example, this works if X is an ample family, it's line bundles, or X has the resolution property, or X is a separated algebraic surface, et cetera, et cetera. All right. So by the way, that means if you can find a scheme that has some class that is not the class of an infinite Azumaya algebra, it cannot have the resolution property. So that was one thing we tried. We were trying to figure out if there's a way to show that something doesn't have the resolution property this way. We weren't able to find any counterexamples beyond existing counterexamples. So in summary, when you allow affine pure maps instead of finite flat maps, and you allow infinite rank twisted vector bundles and infinite Azumaya algebras instead of the traditional ones, you can show that many things that we don't know, understand in the finite rank case, do have twisted vector bundles of infinite rank. We do not yet have a good counterexample that would show that we don't have good counterexamples beyond the existing counterexamples. That's one of those open questions. And I think this question about lifting vector bundles and finding an obstruction in codimension 2 is also sort of a weird, fascinating feature of this. So if you want to understand better what's going on, you can look at the paper we put on the archive and see many other examples of incredibly bizarre phenomena I didn't get a chance to tell you about. Thank you.
All right. Thank you for this fascinating talk. Questions?
If your class is actually torsion, what do you get in this case? Do you get an actual Azumaya algebra, or do you get something infinite dimensional?
You still get something infinite dimensional, and it's still an interesting for a non. If you take a smooth threefold, it has an ample family of invertible sheaves. So for a smooth threefold, for example, there's always going to be infinite Azumaya algebras, even though all the cohomology is torsion. Well, all this tells you is that it's possible to show that there's infinite rank vector bundles without being able to show that there's any finite rank vector bundles. It's just one of those weird things. And you might hope, you can write an infinite rank thing as a colimit of finite rank things and try to improve the locus where it's locally free. That we haven't figured out anything like that that makes any sense. Thank you for asking that.
All right. Any other questions? Well, let's.
Bert unmuted himself for a second and then remuted himself.
Well, I was going to ask, let's see. Are there still non-separated counterexamples? Say.
Yes, in fact, the edit and Hassick-Fresh Vistali counterexample is still a counterexample. It doesn't have an infinite rank one either. Thank you for asking that.
Okay. Anything else? Okay, let's thank Max again. I'll stop the recording.